If you're in a free-falling elevator, you won't feel your weight. In fact, you can't even tell if you're falling or just floating somewhere in gravity-free deep space. Now, Newton explains that of course there is gravity. You do have your weight, but it's just that the force adjusts itself by some mysterious coincidence in such a way that everything falls at the same rate. That's why you get the illusion of being weightless. And Einstein comes along and says, what if there's a simpler explanation? Maybe there is no gravitational force, no mysteries. What if they're actually floating in space and it's the ground that's accelerating up? Now, this is elegant, but there's a big problem with it. The problem is Earth is round. So if the ground is accelerating up, does that mean that the Earth is expanding? Well, clearly not. That can't be true. So what's going on?
Who is running faster in these two clips? When I say, well, Einstein, actually, they must be running at the same speed. It's the same clip. You have slowed this one down. And Einstein says, exactly. Just because you see something slower doesn't mean that the speed is less, isn't it? Here, he's running slower because the time itself has slowed down. Not because his speed is less, his speed is the same, but the time has slowed down. Maybe the same thing is happening over here. Maybe the light is traveling at the same speed, but the time over here has slowed down. Therefore, the light travels less distance, but in less time. And that way, the speed can still be the same, isn't it? And looking at this, I say, well, Einstein, you basically come up with stuff just to ensure that your speed of light postulate doesn't break. And Einstein says, yes, that's what we've been doing since our special relativity days. But let's think about what this means. This means that clocks at different heights should run at different rates. Clocks which are higher should run faster, and the clocks which are closer to the ground should run slower. So we have time dilation, a different kind of time dilation. This is called gravitational time dilation. And what's interesting about this is that since your head is slightly farther away from the ground compared to your feet, your head is actually going to get older older than your feet by 1 second every 100 million years. So this means the time difference on Earth is very, very minuscule, which is very convenient for Einstein. So how exactly does the gravitational time dilation allow the ground to accelerate up without the Earth having to expand?
Well, for that, we'll go back to Epstein and his book, Relativity Visualized. He says, well, Mahesh, since this is a theory of space and time, well, let's draw a space-time diagram. Now, remember, in this space-time diagram, everything travels at the speed of light. For example, when objects are at rest, let's say when an apple is at rest, it's rest in space, but it is moving through time with the full speed, the speed of light. Since it's moving through time, 1 second in my clock will be exactly the same as 1 second in that apple's clock. So its proper time ticks at the same rate as my clock because it's completely moving through time. So 1 second, another 1 second, another 1 second, another 1 second. Look at the clock over here, another 1 second. We'll stop over here, okay? Now, what if the apple was moving, say, a little bit to the right in space? Well, in that particular case, some of its velocity is diverted to space, and now a little bit of its velocity is diverted through time. So it'll start ticking slower. Let's look at it. It's going to go like this. But remember, that vector should have the same length because this is the speed of light. Everything travels at the speed of light. Okay? And as a result, you can see its time, the time over here, its time is less. It's ticking slower compared to our clocks now. So, after 2 seconds in our clock, it is still less. You can see, it'll keep on doing that. And after 5 seconds have gone in our clock, look at its proper time. Its clock is showing how much? Well, let's look at this. It's showing a little bit more than 3 seconds. Now, this is nothing new. We've done this before. But there are 3 important things that we need to understand from this. 3 important features of this. The first is that this length and this length will obviously be the same. Which means the path length in this space-time diagram will always stay the same. The second thing is that that path length represents how much time has ticked in our clock. To understand how much time has ticked in their clock, their proper time, you need to look at this axis. So, for example, its proper time is so much, which is the same as our clock because it's completely moving through time just like us. But look at this one. Its proper time is only so much because it is moving through space. And third, if the paths are a straight line, that means the velocity has remained the same direction, which means it's not accelerating. So straight lines are non-accelerating paths or inertial paths, which means if something is accelerating, it would be curved. That's how we would know it's accelerating or not.
Let us look at the ground. What will be the space-time path for the ground? Well, if I get rid of everything, well, the ground is at just rest. It's not moving through space. It is just there. Therefore, the ground should look like this. But let's see what happens when you open it up. Here I have it. I open it up and boom! What do you see? The ground is curved. It means the ground is accelerating upwards. And now let's think about another patch of ground on the opposite end of the Earth. It'll also be accelerating. I'll just do a mirror image over here. It'll be accelerating the other way around, but these 2 patches of ground will not be moving away from each other. The Earth will not expand because when you fold it, look, in our spatial and ordinary spatial and temporal terms, when we see it, how we experience it, the distance between them stays the same. Why is that happening? It's happening because of curvature of time, because time is curved. We have discovered curvature. So this is how time dilation, which causes curvature, allows your ground to accelerate away, and yet, when we see it, Earth will not expand. Finally, comes the question, what does it look like when I put an apple over here? So let's do that. Here is going to be my apple. According to Einstein, this apple will not accelerate. It's just going to stay in put. So let's say it's at rest because it's going to be inertial. If it's at rest, then it will be only moving through time. And look, the time at this place is somewhere upwards. So it'll move through time, wherever it is over here. It'll move through time and it'll continue to move through time only. It'll go like this. It should continue straight line. This is how it will go. So this is what's happening according to Einstein. And now let us see what happens in our spatial and temporal terms as we see it. As we see it, what do we notice? We see the apple falling to the ground. That's what we see. The ground stays put. The apple is falling to the ground. We see it. We observe it accelerating to the ground because we see it to be curved. But guess what? It's not. It's going in a straight line. It's the ground that is curved. But again, because we inhabit a curved space-time, because of it, the ground appears to be at rest and the apple appears to be falling. So putting it all together, because we see ground to be at rest and apple accelerating down, Newton thought, well, that's basically what's happening. The ground is at rest and the apple is accelerating. But then because of all the discussion that we thought, Einstein realized maybe that's not the case. Maybe it's the ground that is accelerating up and the apple stays put. The equivalence principle. Now, when the moment we do that, this is how we start thinking about it, right? And as a result, we start wondering, well, if that is the case, then why doesn't the ground, if the ground is moving upwards, the ground is accelerating upwards, then shouldn't the earth expand? Well, the problem is this is not the right way to think about it because you haven't considered the curvature of time, which is important if you're using Einstein's theory. But when you do incorporate it, you actually see that yes, ground can accelerate up. The apple is inertial, but when you see it in the ordinary spatial and temporal terms, notice ground is not moving anywhere. It just stays put and we see the apple falling down. It all works out. Do try this at home. You just need some pen, paper, and scissors and do ponder about it. Because think about where did this all come from? It all came from that one ancient age-old experiment, why things fall at the same rate. And I find that absolutely fascinating. So it's the time curvature, folks, that is responsible for almost all the effects of gravity that we see in our everyday life.